No, that's not duality. With the duality, you can treat greater than constraint.
Oh,
Okay. Apologies to our viewers for doing something else. Well, there aren't any at the moment. Question 2. Would anybody volunteer a solution to be gone through hard and nasty, like last week?
Yeah, everyone enjoyed this sort of thing. You will watch it, it's like but I needed it happening to me. I only got 2 questions. I did question 2A, but I don't think it was consistent with what you'll be wanting. And then part B, I did so much, but I don't know if it's again.
Shall we have a look then?
Yeah.
I reckon.
There you go.
So this is the best though. This is what ideally there would be like 6 of you,
Mm.
and each of them would show the solution.
Yeah.
And each of them would have the so that we know what the common mistakes are, because the common mistakes are basically all the mistakes that you make are common because they're in these small numbers. One of them makes that mistake, it's already a 6th of all students. Okay. So question 2, what is the definition of a subgroup, and what is the definition of the order of an element? The term subgroup is a group or groups that belong to a larger group. H is a subgroup, it's in 2 or more subgroups. H is a subset of G when the group operation of G is restricted to H. There exists a trivial subgroup consisting of the identity, element, and nothing.
As in that, there's nothing else in that.
Yes. Okay. I don't know where to start. This is. I'm thinking of Julian's answers, which are very philosophical always, but not so much down to earth. So. Okay, so perhaps I'll get philosophical. So what is the purpose of a definition? So the purpose of a definition is that you create some sort of an abbreviation. It has to be very definite as definition, definite, so that when you see it, you recognize whether it is that or not. Okay, so it has to have very clear criteria by which you can determine whether an object is what the definition says or is not it. Okay. So the simpler the definition, the better, and it should just state the criteria. Okay. Right. Now, unfortunately for you, Jordan, when you start writing things that are not required, you spend time writing things that are not required. And it's not a bad thing if you give an example. Like there is an example, okay, that's true. It's true. Yes, but that's not what defines a subgroup. Okay, that's a statement. This thing, it's a theorem. This is always a subgroup of any subgroup of any group. So it's not part of the definition. So you don't have to write it. I mean, I'm not saying it's wrong. It's correct. It's a true statement.
Mm-hmm.
But it isn't just part. It's just not part of the definition. Okay. Now here, the term subgroup. Well, belong to a larger group. Okay, so now you're writing about the term subgroup and what it's used for, but that's not the definition. Okay, I don't know. H is a subgroup consisting of 2 or more subgroups. That I don't understand what that means.
Well, it has to at least have the identity and its inverse at some point. Any elements inverse.
Yeah, but what do you mean? So H is a subgroup consisting of 2 or more subgroups. I just don't know what that means. So
actually, I think the way I wrote it, I just realised that that doesn't make sense. I was meant to.
You meant 2 or more elements.
No, I was meant to put that H in G. No, let me get this right. The subgroups in G have to be at least 2 or more. I'm trying to word it in my head now. It sounded a lot better on paper. No, it was. But basically, you can't say that a group is a group without at least two subgroups.
That's not true, is it?
That's not true now.
So I don't know. Like this group is a group. It only has one subgroup.
Yeah.
Well, okay, it's the only group that has
The trivial.
to isomorphism. It's the only group that only one subgroup, but still. Okay, so the key things are there actually. So H is a subset of G. Yes.
When the group is
When
the group operation G is restricted to H. So that's definitely right.
Well, I'm thinking about when. Yeah, and the group operation of G is restricted to H.
Yeah.
So kind of H is a subgroup of G. Well, one wants to say means, but one says if. If H is a subset of G, let's say I put and rather than when, because when doesn't sound right in this sentence. So that if you wrote this bit answers the question. Okay, the rest of it is extra, or doesn't make sense as a previous. Okay, so for you it's a matter of I keep saying that, and I shouldn't be saying it in public, but just focusing on the substantial in the question. Just narrow it down to the minimum, kind of the shortest possible answer that addresses what the question is asking. Okay? In this case, the shortest possible answer that addresses what the question is asking is exactly that sentence. Okay, so it's actually the defining sentence is the one you wrote, and in some kind of style, one should put the beginning of the definition, but that's the term that's being defined. And that answers the first bit of part A. Okay? Makes sense?
Yeah.
Now it also wanted to define the order of an element of a group. So that's the thing.
Completely wrong.
Yes, that's a. So there are two things. There are two different meanings of the word order, or meaning. I mean, two different situations in which you use the word order in group theory, which is slightly confusing, perhaps. So there's the order of an element of a group, and there's the order of a group, which is a different thing.
Yeah.
So the order of a group, unfortunately, people started using it in that way, is how many elements the group has.
Yeah, what it consists of.
Yeah.
Yeah.
Well, the group has elements. I don't know what it consists of. You could say consistent, but how many elements it has?
Yeah.
Okay. The order of so the definition we had was it describes something else. Okay, this is I'll continue here.
Yeah.
The order of G is, so the definition that is given in the book is that it's the least positive integer k, say, doesn't matter, which satisfies that G to the k is the identity. Yeah, that's the definition given in the book. Suspect the definitions one has to memorize for pure maths exams.
I just scrolled that down while you were writing it.
The order of G is the number of times known can be operated with itself before returning to the identity. It means the same, but
yeah. Okay. Right. Okay.
Because you could start interpreting it in different ways. What does it mean operating on itself?
Yeah.
This is clear.
Yeah.
Well, as long as you say that G to the k is G times G times G times G times k times, but that I think we know and we've been using all along. So It's all right. Okay. So this is so the meaning is the same, but this is much more precise.
Okay.
And that's the confusion, because the size of the group G is called the order of G,
Yeah.
of the group G.
I think this is why I was struggling with it, because
Yes.
I think the two definitions that I had in my head were sort of
they kind of
conflicting
mix there.
Yeah.
Because if it was strictly just a cyclic subgroup, technically what you've written there would be right as well. Or sorry, a cyclic group.
And then the number of all different G and G is the size.
Is the size of the group G.
That is true. But that doesn't address because there you're addressing. Well, that is true, but that's kind of trivial, so nobody would really write that, because we know what the size of a set is. It's the number of elements. If it's finite, if it's infinite, it's kind of more difficult, but it does exist, these notions, these kind of analysis of infinite set. I'll make it a bit, zoom out a bit. Okay, but the order of a group is the size of G, the number of elements of G. Yes, but that has nothing to do with the question you actually asked.
Yeah.
So the order is defined like this, but at the same time there's like a side remark. So we had this definition, but one could have an alternative definition perhaps, in which there is this group generated by the element G, which takes all powers of G. And the order of this subgroup generated by G is the same as the order of the element.
Yeah.
Okay. So in the way we did it, it was a theorem. But if somebody else wanted to do that, they could define the order of the element as the order of the subgroup generated by that element.
Right.
Because they're the same number every time. But we didn't. So we stick with each positive integer such that G to the K is E. That clear? Sorry, I need a sip of water. Starting to dry out. I'll criticize my solution. What did I write? A subgroup of G is a subset S, which is a group with the same binary operation as G. Oh.
I just rewrote the question. Wait.
So I was wrong. Now I realize I was wrong. It's a subset of G, and the group operation is restricted to H, and H is a group. So that's kind of missing. So you see, I can mess it up. You have to say that H is a group. That's the crucial thing. It has to be a group. If you just take a subset and put the operation on it, that's not necessarily a subgroup, because we have these things. It has to have the identity, it has to have all inverses, and it has to have all products in it.
Like you said, H of G is closed.
For the benefit of cloud viewers.
Yeah.
There's a subset of... No. One doesn't say that. One says it's a subset of G. Which is closed under the group operation. That is, I think, just good enough.
Yeah.
Because what does it mean to be closed?
I only use it in the reference that we've used it.
Yeah.
It's like that's what exists.
But so the thing is, you go. It's kind of it's a philosophical question again, but you're building it from small things.
Yeah.
So you don't say closed first. First, you say it means, and then you say, oh, in these cases, we say it's close.
Yeah.
But yeah, I think that's just about okay. But ask Killian. Yeah, so this is what I realized. You have to put that kind of closing mix. So in fact, this. I mean, again, if I wanted to be completely strict, that's a theorem-ish, because the definition was it's a group, and it's a group with this operation. You can prove that it's if and only if for any two elements it contains a product and it contains all the inverses. Okay, it's one of the theorems. So the definition is it's a group, the operation is the same, and it's a subset of that. Did I get it right? It's a subset, which is a group with the same binary operation. Well, shouldn't be. So maybe I didn't get it right. Same as G, restricted to H. Okay, I think the other one I got right. Stop doing this. Focus. Okay. Good. What's part B? So part B doesn't have a question for a long time, which I think you discussed yesterday. There's no negative, it's supposed to be positive.
Yeah, and I was there, I was reading the top bit, and I just went, oh, it's a statement. And then he looked down and went, there's the actual question. Said, like, just as in the exam, all here from behind me. Oh! I turned over the page. There's the question.
Okay, so what we're supposed to prove is that if you have a cyclic group, and any subgroup of it is also cyclic, and in fact, we're supposed to show that it's cyclic because, so cyclic means generated by one element, basically. And we prove that it's generated by one particular element, defining. Okay, that's the meaning of the question. With that, it's actually that's a hint. How do you prove that it's always cyclic as a subgroup of a cyclic group? Aha, this is how you just solicit it. So that was the statement of the question repeated. Now, okay. So far, so good. H is a subgroup because there are many, typically. And each of them, has to be cyclic. That's what we're trying to prove.
Yeah.
If it's then trivially cyclic, that's both. Yes. Then G can be written as for some integer k. It's also the H, K minus K positive. You can assume that H contains only positive powers of A. No.
Did you turn it over before? Yes.
I'm trying to think what that where that's heading. Okay, so K and minus K are not positive, right? I mean, if K is positive, then minus K is not, and vice versa. I don't know or not. Where that comes from.
No.
Okay, so what? Well, we can't really assume that it contains only positive powers of A. We can assume that every element is a positive power of A. Okay, it's kind of so well, it actually, the text already gives it away here, right? It says it's a to the 0, it's a to the 1, a to the 2, 3, 4, all the way to n minus 1. And if you take any other power of a, positive, negative, no matter what, it's always going to be one of them. Yeah, that's the idea. But this is a bit okay. So k and minus k are positive. That's right, false. But yes, we can somehow assume something. We can assume that every element is one of them. Yes, turn right. You're right. I shouldn't spend too much time on that. Let L be the smallest natural number system. Yes, the way of finding H is A to the L is a generator for H. That is exactly what we are supposed to prove. Yes, excellent. What is H dashed? Okay, I think there's one sentence missing. Let H dashed be an element of H. Something like this. Because you don't say what H dashed is. Anyway.
Yeah, I just implied since H dash is in H, so let H dash be an element of H, and then H is.
Yes, that's yeah. So that what we can. That's just that's the idea is right.
Yeah.
So I take H. So yes. So the idea has to be. I'm trying to prove that this H that I've just defined, A to the L, is a generator. Okay. So to prove that, I have to prove that any element in H is a power of this element. Okay. That is the definition. Okay. So I take any such element, H dashed, and I'm trying to prove that it's a power of A to the L. Correctly, it says yes, it is in G, so it must be one of them here.
Yeah.
Yeah, because it's in G. So yes, so it is indeed A to the K for some integer K. Using the division algorithm, I think there, in fact, you need less than.
Strictly less than.
Yes. The remainder is always less than the divisor.
Yeah, it is.
That is crucial in this proof. So A to the K is A to the L Q plus R, so that's AL to the times A to the R, which is H to the Q, A to the R. Yes, and now A R is down that. That is not right, is it? And I believe this goes the other way around. So this is H to the minus Q, A to the K. But it doesn't change the conclusion that if AK and H to the minus Q are in H, are they? Yes, A to the K is H dashed, yes, so it's in H. This one is also in H. AR must also exist in H. However, L was the smallest positive number of AR. So R. Now we're doing it. So L was the smallest positive integer, so that A to the L is in H. Okay. And now you have to say, now you can't say if R equals 0. If R equals 0, then yes, then everything is brilliant. But now you have to prove that R equals 0. This is where that comes into play.
Yeah.
So L was the smallest positive integer, so A to the L. A to the R is in H. R is less than L. R is an integer, it's less than L. And A to the R is in H, and L was the smallest positive integer. So the only conclusion is that R can't be positive.
Right.
So R has to be 0.
Right.
Yeah, that's where this is needed. Because if it was non-strict, R could still be L, and you still have improved everything.
Yeah. Okay.
Yeah. But because L is the smallest one, and R is less than L, strictly less than L, so it can't be positive. If it was positive, an A to the R, then it would have to be at least L. Yeah, but it's not. Okay, so it has to be 0.
So it's rather than if, it's to say.
So,
I would say
and
therefore.
yes, that's correct. Yeah.
That'd be worth the 8 marks.
Oh, I'm not marking it now.
Good mark the presentation either.
No, not 8.
Oh, thanks.
7.
7. Oh. Better than the kick of the 2.
Okay.
That's all.
Did you write anything? No,
I was going to say, do you want to use this?
No, I am. Okay, so what did I write? Now the next one I messed up.
Oh, yeah, that.
No, the next one. Okay, so I think I wrote wrong. Okay, we're trying to prove this. G is a. Oh, what did I put? Yes. So actually, I put that. Yeah. Oh, now whether that's necessary. And this one is quite interesting. So we're trying to prove this. So I'm trying to prove that every element in there is an H and every element in H is an F. The Euro proves that every element in H is an F. Every element of this being in H is almost true. That's okay. So AK is in H, and therefore every power of AK has to be H. So that's almost redundant. And then I wrote this. That's a good thing. With the remainder, this is this. So AR is H, but R is K in case it is positive. So R has to be 0. Same as what Jordan wrote. Not much more time. Bit more time. That's okay. So prove that A to the M equals E if and only if N divides M. Nobody got there?
No, I didn't get down to that. Spelling 2 on that.
So what does one want? Okay, so just to realize. Don't start writing anything.
No.
What it means that N divides N. Don't start writing anything with the. Let's just concentrate on the shortest answer that will do. Okay, the shortest answer is it's proving that if and only if. Yeah, proving that if and only if. In most cases, means proving if and proving only.
Right. Okay.
So this is an equivalence. An equivalence is a conjunction of two implications. So prove that if this and that, and second you have to prove that if this and that. Sometimes you can go directly and say, we know this is equivalent to this, and this is equivalent to this, and this is equivalent to this, and give you everything. But most of the time, you split it into these two things. If this, then that and this. I think that's what I did. So what I wrote was, if N divides N, okay, that means that. So then we're trying to prove that A to the N is what? I forgot the question in the meantime.
A to the M is equal to E.
Yeah, A to the M is equal to E if and only if, yeah. So if N divides N, then that means E to the N, then this is like this.
Yeah, that's implied, yeah.
Well, you should still have.
Yeah, definitely.
Because we know that A to the N. A, and then So this is one way. And then back the other way. Is A to the n of b. Then now we need to use division. But it's actually the same idea. So all is there. So again, E is A to the m. But m divides like that, which is like it before. So this is the end. And we will left with A to the because this is the identity device. Well, this is the other by 8 of order n. And again, we have r is less than n, equal. Okay. But n is the order of a. It's the least positive integer such that a to the n equals the identity. And this is smaller, so again, it can't be positive. So r is 0, so the remainder is 0, so it's divisible without.
Where is the j coming?
It's j. That's a semicolon.
Oh, right. It's because there's
it's
going further as well. It looks like there's another j. So I thought,
AR to
Yeah.
sub
right, now it's
okay, yeah.
Like semicolons. So there are two semicolons and no j's now.
Yeah.
Okay, that's the most important general idea here is the two implications. The next one,
Part 3.
part 3, I messed up.
Yeah.
So I'll take Killian. So Killian has a very succinct solution here, which I tried to pass during lunch today. Okay. So what we're trying to prove is that, okay, first we should read what we're trying to prove. Well, I'll try to stick them both there. Yeah. So we're trying to prove that the order of B is n over D, where D is the greatest common divisor of n, the order of the group, and R, which is the exponent defining D. It's a theorem straight from the book, so you can read the proof from the book, and if you write it word by word, you have full marks. Okay? Killian right is, well, just repeats the definition of the order of B. So forms m to the b and b, but b is a to the r, so a to the smallest m such that s is equal. And now he's using part 2. A to the Rn is E. If and only if n divides up to Rn. So this is the smallest n such that n divides Rn. Like that part. But now, n divides Rn, because D is the divisor of n. N divides D, if and only if, sorry, n divides Rn, if and only if n over D divides Rn over D. So if this is a multiple of n, then this is a multiple of n over D. N over D is so now here with n over D is called private to R over D. Again, by definition of D. So n over D divides this whole thing. This is like n times R over D. But n over D does not divide R over D. So n over D, well, but one time, n over D is divided with at least n over D. and then the C rating. So if you're looking for the smallest positive n, such that n over b divides n, well, smallest term. I don't like this book very much. I don't know. I'll look in the book. You should look in the book and see what they give. Okay, but that's the book. But I mean, we're spending too much time on it because it's a theorem straight from the book, and you're expecting all of it straight from the book. It's true. Well, for full marks, of course. I mean, for passing, you're expected to do simple things only. But, for full marks. Okay, and then the remaining 5 minutes or 10 minutes. Illustrate these results. Okay, so this is my least favorite question. Okay, so this is something that even if you don't know the proofs, then probably you'll be able to do something like that, right? Because it's just saying what does that mean in this group? What does that mean in this group? What does that mean? So if you take the cyclic group of order 20 out of 1. So illustrate all these results. All the subgroups. Okay? So it wants you to list all the subgroups of the cyclic group, and it also wants you to list all the elements. So what are all the subgroups? Well, there you go. Part 1. There's that. The subgroup has to be cyclic like this. That already gives you a list over here. List already generated by E, generated by A, generated by O squared, generated by O cubed, generated and so on, all the way to A. Yeah, so you can just kind of like that. Well, yeah. So kind of can do. Now it's 20 different groups, and they're very many elements, and some of them are going to be the same. So now for each, so okay, so you can list like, I don't know, do it any way you want, but you can say, okay. I started and I realized I was being silly. I think there was a submission problem or something like that that looked similar to this. One of the exercises we were doing. So, now here I'm illustrating the other theorem with the GCD, the other statement, GCD. But then you soon realize that actually the orders of them, if they have the same order, then they're actually. So, for example, this one is generated by A to the 6th. But in fact, it's the same one as the one generated by A squared. So here I've listed them in the order in which they would come, but it's probably going to work.
So, what would you say that both 2 and 6 belong to? So,
I don't know. I wrote it like this. I would say this, and then in the end, I gave up and I only did this. So you kind of get it. I mean, 19 is cosine with 20, so that could have to be so.
Any of the elements.
So GCD is 1, so the order is 20.
Any of them are 5 would be cosine to it.
For each divisor is. The GCD of 14 and 20 is 2. It's going to be the same group as. The GCD of 13, so it's going to be the same as 1 generated by 8. So 11, 13, 19 are co-prime, 17 are co-prime, so if they give you a notebook, which you see as 1, the order has to be n.
Yeah.
And actually, there aren't, they have exactly one, the cyclic group has exactly one subgroup of each group. So the GCD of this number and 20 determines which one it will be. So let's have a look at what Killian number.
So when you put order 20 over GCD, then the number by 20, and you've got equals, and then the number, you have 10. Does that mean there's 10 elements in that group?
And that's a group.
In that subgroup? Say, so what would you get?
So Killian put like this.
If somebody is present, if some of these present. Yeah, just understand the protocol, yeah.
Partial credit if some of these present probably means that you get some marks if you don't list everything. But yeah, so I don't know whether my question to him is right. Okay, well, this is too complicated. You should have listed it in like S3.
Yeah. Like I said, you wrote every single one.
Yeah, I did, but some of them multiple times.
Yeah.
Yeah.
Like
So you see, so this answer does not conform to my criterion. The least work that would do. This one does. So in this sense, this solution is better than that.
Okay.
We did it. Goodbye.